Hello and welcome back to Machine Learning. I'm Javita Christie, and in this video, we are going to talk about discrete probability distributions, namely the binomial distribution and the Poisson distribution. And as well as we are going to see Bernoulli's distribution. So let's begin. We are going to start with the Bernoulli distribution because this is the distribution that is just like binomial distribution. In fact, binomial distribution is a special case or a type of Bernoulli distribution. So when we have a situation where the outcome of a trial is withered success or failure, then the behavior of the random variable x can be represented by the Bernoulli distribution. So if you have a situation where there is either winning or losing, success or failure, if the problem is of that kind, then it would be a Bernoulli distribution. And such trials or experiments would be termed as Bernoulli distributions or Bernoulli trials. And we can derive that a random variable x is called a Bernoulli random variable with parameter p when it's PMF. Now here PMF means the probability mass function. When that takes the form of this, which is px of k is equal to px equal to k, which is equal to small p raised to k in bracket 1 minus b raised to 1 minus k. So if your probability mass function takes this kind of a form, then that means that random variable is called a Bernoulli random variable. Here the value of k will be 0 and 1, given that there are two states, success and failure, or winning and losing, but always two states. It could be heads or tails as well. Now the probability or the small variable p is always going to lie between 0 and 1, 0 and 1 included. So using this, you can find out the CDF, which is the cumulative density function, which is denoted by fx of x. And this can be expressed for the Bernoulli random variable as this. It is equal to 0 when x is less than 0. It is 1 minus p if x lies between 0 and 1, including 0 but not 1. And it is equal to 1 when x is greater than equal to 1. The mean and variance, if you want to calculate for a Bernoulli random variable, they can be calculated like this. Mu, which is the mean, it's also sometimes written as E of x, is equal to small p. And sigma square, which is your variance, is written as VAR x, which is p into 1 minus p. And here the probability of success is p and probability of failure is 1 minus p. So wherever you see the small letter p or the lowercase p, that means it is a probability of success. And 1 minus p naturally would be the probability of failure. Now let's take a look at binomial distribution. So if you have n independent Bernoulli trials and x represents the number of successes in those n trials, then x is called a binomial random variable. So binomial distribution is very much closely related to the Bernoulli trials. Okay, so if you have not one Bernoulli trial, but several Bernoulli trials, and in this case, n independent Bernoulli trials, then x is going to be the number of successes in those n trials. And so you can call x as a binomial random variable. And so that's the reason why a Bernoulli random variable is a special case of binomial random variable with parameters 1 and p. Let's take a look at what the PMF, the probability mass function of x, would be if the parameters n and p are given. It would be this. So you have px of k, which is equal to px equal to k, which is nck, which means n combinations. This is a formula for combinations. So nck, which is p raised to k, 1 minus p raised to n minus k. So this is a slightly different formula than what we saw for Bernoulli's trials. And here the values of k can range from 0 up to n. In Bernoulli's trial, we had only two states, either success or failure. Here you can have multiple trials, and that's why the value of k is from 0 to n. And here p, lowercase p, always lies between 0 and 1, and 0 and 1 are included. And if you want to know what is nck, that is n factorial divided by k factorial into n minus k factorial. This is also called the binomial coefficient, which is the number of ways to choose k items from n. So this is an equation for nck, which is n combinations of k. So choosing number of ways to choose k items from n different items. Now, let's see some examples. So if you toss a coin n times, then capital X is your random variable, which would belong to any values from 0 to n, and let that be the number of heads. So if the probability of heads is lowercase p, then we say that X has a binomial distribution, which can be written as X, bin, and then n comma p. And the corresponding CDF, which is the cumulative density function of X, is this value, which we just saw previously. Only here you have this extra formula that X should lie between n and n plus 1. And the distribution has the following mean and variance. The mean is NP, and the variance is NP into 1 minus P. So the important thing here is to remember these formulae, because later on you can solve examples using just the formula that you remember. So let's now take a look at some examples for this. So there is an e-commerce company called Fashion Trends Online, or FTO, and it sells women's apparel. So it sells women's clothing item, and it is observed that about 10% of their customers return the items that are purchased by them. And the reason for return is, can be size, color, material, anything. It's not up to the mark. It's not what they wanted. So on any particular day, 20 customers have purchased items from FTO, Fashion Trends Online, and you need to calculate the probability that exactly 5 customers will return these items. Okay, so you're already told that 10% of customers, it is observed, are always returning items. So probability of customers returning something is 0.1. We should remember that. And it is now also told to you that on one particular day, when you are supposed to calculate this, on that day, there are 20 customers who have purchased something from FTO. And your question is to find out exactly how many customers will return items. Exactly 5 customers, probability of exactly 5 customers returning the item. And we are going to be using this formula right here, which we saw previously. I've just kept it here for reference. Okay. So we are just going to be using this this formula here, and the formula states that you require the values of P, N, and K. So we are going to see how you can equate those values here. Okay. So first of all, you need to remember that in this case, what we are trying to find is the probability that X, which is our random variable, is equal to 5, because we want to find exactly 5 customers, probability for exactly 5 customers to return the items. And this would be equal to, you see the value here, NK. We will be ignoring the sigma part of this formula, because sigma is not required since it says exactly 5. Okay, so remove the sigma part, and we need to do NCK. N would be the total number of customers that have purchased, which is 20. Okay. K would be this value of X here. So that is 5. And this is what we have. Now, small p is going to be the probability of people returning the item. So returning the item in this case is 0.1. because we are given in the question that it is 10%. So this is 0.1 and raised to k. So the value of k is 5. Okay. So if the probability of returning the items is 10%, then the probability of not returning the items would be 90%. So in which case we could have over here 0.9, which is the remaining probability, and n minus k, which is going to be 20 minus 5, which will be, of course, 15. And if you evaluate this, remember the formula for 20C5 and evaluate the whole equation, you will be getting this value 0.03192. Okay, you can verify this for yourself. So this is how you can answer this type of a question. Let's take a look at another one. So in this question, we are asked, what is the probability that maximum 5 customers will return the items? Okay, so this is slightly different than previous question where we were asked exactly 5 customers. Here it is maximum 5 customers. And to show this, you need to, instead of ignoring the sigma sign, this time we are going to use the sigma sign. And to use the sigma sign, you need to use P of x less than equal to 5. Okay, and then this would be equal to, use the sigma sign. So using the sigma sign, you're told that maximum 5 customers, which means it could be 0, 1, 2, 3, or 4, or 5. So our sigma will have k equal to 0 up to 5. Okay, and once again, probability of returning something is 0.1, and this will be always raised to k. And probability of not returning something is 0.9, which will be raised to n minus k, which is 20 in our case. Let me just erase that. This is going to be 20. So 20 minus the value of k, so whatever is the value of k, and then you can evaluate this expression as well, and the answer you will get is 0.9887. Okay, you can verify this on your own. So this is your the second type of thing you can answer. Let's take a look at another type of thing. So this says probability that more than 5 customers will return the items. So in this case, more than 5 could mean anything. It could mean 6, 7, and up to infinite number of values. So what kind of value would you put here in k equal to 0 up to n? What are you going to take place as the value of n? So you don't want to put infinitive, but you have a very simple thing that you can do in this case, and which is that probability of x being greater than 5 is actually equal to 1 minus probability of x being less than equal to 5. And we have already calculated the answer of this thing, x less than equal to 5 in the previous question. So you just need to substitute that here. So 9887, and that should give you 0.0113, and that's your answer. Let's take a look at the next one. What is the average number of customers who return the items? Okay, so average would mean that we want to calculate the mean, and the mean is calculated using this formula right here, which says mu is equal to EX equal to P. Okay, so it's just the value of P, and that's very simple. So calculating the mean is pretty much straightforward. And in this case, it will be equal to mu is equal to n cross P. Actually, the value of mean is not P, it is actually n. So n into P, and the value of n into P is 20 into P, which is 0.1, and that would give you 2. So that is the answer over here. 20 into 0.1 equal to 2. And let's proceed to the next one. This time, what are the variance and standard deviation of the number of returns? Now, once again, a slight correction in this formula, you need to add the number of trials here. So NP into 1 minus P, that is your variance. And the variance is going to be 20 into the value of P, which is 0.1, and 1 minus 0.1, which will be equal to 1.8. And you are also asked to find the standard deviation. So this is the variance sigma square. The standard deviation is equal to 1.8 square root of 1.8, which will be 1.3416. You can verify. So this is the standard deviation and variance. And this is how you can calculate binomial distribution. And here is a simple histogram of what a binomial distribution looks like. So you can see that this distribution has this type of a histogram, and this histogram has been created for n equal to 6 and probability of success being 0.6. So this is the histogram that gets created. Now, just like binomial distributions, you also have multinomial and multi-Newly distributions. So binomial distribution can be used to model the outcomes of coin tosses or for experiments where the outcome can be either success or failure. But if you want to model outcomes of tossing a k-sided die, which has 6 sides or something like that, or experiments where outcomes can be multiple, then you can use multinomial distributions. So binomial distribution is only for 2 outcomes, but if you have multiple outcomes, you can use multinomial distribution, and you can define it like this. You can have x, which is a random variable, where xj is the number of times side j of the die occurs, and to calculate the probability mass function, you will use this formula. So you can see it is slightly different than the previous one, so it's much more complicated. And here, all these states of x, all the outcomes of x that will form n, and the multinomial coefficient is defined as n factorial upon x1 factorial, 2 factorial, up to xk factorial. And the summation is over the set of all non-negative integers x1, x2, up to xk, whose sum will be actually n. And now consider a special case of n equal to 1, which is like rolling a k-sided dice once. Okay, so x will be a vector of zeros and ones, like a bit vector, in which only one bit can be turned on. So it is a special case, but this special case contains only n equal to 1, which means you're rolling the dice only one. Previously, we talked about rolling a 6-sided die multiple times, but if you want to roll the die only once, then this means you can the dice is going to show up base k, and the case bit will be on. Okay, so it is a bit vector where only one of the bits is 1 and rest of the bits are 0. So you can consider x as being a scalar categorical random variable with k states or values, and you can encode it in this manner. So you can see here, this is an encoding of x. For example, if k is equal to 3, then this would state that 1, 2, and 3 can be encoded in this manner. 1, 0, 0, second one is 0, 1, 0, and 0, 0, 1, which means suppose you have a die that has only 3 sides, then you are going to encode it in this manner. This is also called one-hot encoding because we interpret that only one of the k wires is hot or on. Okay, and it's a very common special case, which is known as a categorical or discrete distribution. And because of the analogy with the binomial or Bernoulli distinction, Gustavo Lacerda suggested that this should be called the multi-Newly distribution. Now let's take a look at another interesting distribution which is used for discrete random variables, which is known as the Poisson distribution. So a Poisson random variable has a wide range of applications, as it may be used as an approximation for binomial with parameters np when n is large and p is small, and thus np is of moderate size. An example of this is if a fax machine has a faulty transmission line, then the probability of receiving an erroneous digit within a certain page transmitted can be calculated using the Poisson distribution, Poisson random variable. So anytime you have such data where you have something faulty or not working, you could be using Poisson distribution to calculate the Poisson random variable. So this variable is used with a parameter lambda, which is always greater than 0. And here the probability mass function looks like this. You have e raised to minus lambda into lambda raised to k divided by k factorial, where k will be all the values from 0, 1, and infinitive. Okay, you can have any values of k. So this is the probability mass function of a Poisson random variable. And you'll see how to use this when I show you an example. The CDF, which is the cumulative density function, is given by this formula, which is not very much different from this one, except that there is a sigma sign here, which goes from k equal to 0 up to n, just like we saw in binomial distribution, where if you are asked what is the probability of exactly 5 returns, you will be using this. But if you're asked probability of maximum 5 returns, then you will be using this because you have to do the summation. And here is a graph depicting what a Poisson distribution looks like with lambda equal to 2 as a histogram. It's not actually a histogram, it's a sort of a scatter plot where everything is connected, all the dots are connected. So this is what it would look like in a graph. Now let's take a look at an example. So on an average, 20 customers per day cancel their order placed at Fashion Trends online. Once again, you have to calculate the probability that the number of cancellations on a day is exactly 20 and the probability that the maximum number of cancellations is 25. So the question is very simple, that you're given an average number of customers that cancel their orders per day on Fashion Trends Online, which is an e-commerce site selling women's clothing. So there are 20 customers per day, and you need to find out the probability that the number of cancellations would be exactly 20. Okay, so not less than 20 or greater than 20, but exactly 20. And for reference, I have provided this formula right here to calculate the Poisson distribution. So you can see the formula. This is the Poisson distribution formula. And we are going to be calculating this value. So to calculate these values, we need to have the value of lambda given over here. Okay, and we are given the value of lambda already as 20 because that's the number of customers per day canceling. So what I actually want to find is p of x equal to 20. And this will be e raised to minus lambda, which is minus 20, and lambda raised to k. Now k is also 20 because we are asked exactly 20 customers. So this and divide by 20 factorial. I know that's difficult to calculate, but if you calculate it, you will get a 0.0888 with a calculator. It's quite easy. So this is the probability that the number of cancellations will be exactly 20. Let's take a look at the second part of the question, which says maximum number of cancellations will be 25. So we are going to be using this formula with sigma. So it's a cumulative density function. And what we want to calculate is p of x less than equal to 25. And this would mean that sigma would be where k goes from 0 to 25. The value of lambda is as usual, we know. And the value of e is going to be e raised to 20. The value of lambda is, we already know, 20. And let's make that raised to k. And we will divide it by k factorial, whatever is the value of k. Once again, if you calculate this, you're going to get 0.00888. Sorry, it's going to be 0.8878. Okay, let me just remove the incorrect answer. So it's going to be 0.8878. That would be your answer. So this is how you can calculate Poisson distribution, and you can use it to find probability. So I hope you understood all of this. And in my next video, I'm going to talk about distributions related to the continuous random variable. So I'll see you there, and thank you for watching.